back to the channel, and in today's video I'll be introducing to you what we call the operational amplifier, or for short, op amps. That's what we call them for short. So op amps, what do they do? So we use them to typically amplify signals that are too weak and small. So it has more purposes than that, of course. That there are loads. If you can search it online, I'm sure you'll find something. But that's the basic general principle of the operational amplifier. So it looks like this. I'll draw it for you now. So it has two input terminals. It has a non-inverting terminal and inverting terminal. So plus is non-inverting, minus is inverting. It has an open loop gain as well. We just call it AO. And it has supply rails as well. So it could be like plus VCC and minus VCC, or the bottom could even be the ground, okay? The important concept here is that this is the upper limit and this is the lower limit, but these don't have to necessarily be the same. As long as this one's the upper limit, so it must be higher than this one, but this one doesn't have to be the mirror, if that makes sense. And of course, we have output voltage of the amplifier. So let's take a closer look at what we call the transfer characteristics to understand its behavior. So it has two regions that are of interest to us. Well, technically three. We have a linear region, then we have these saturation regions where it's constant. So on the x-axis, we have the difference voltage, VDIF. So VDIF is just the difference of the two terminals. V plus minus V minus. And on the y-axis, we have the output voltage. Okay? So if the difference exceeds this linear boundary, then it saturates at the supply rail limit. So this could be plus VCC, this could be minus VCC. Okay? But let's look at the linear region. I think this is the most important one to understand. So calling back to the straight line equation, y equals mx plus c. Short that bit in meter. Okay, so let's take a closer look at this. So the y-intercept is 0, so we can forget that. The output is the y, so the output voltage is y. The difference voltage is x, but what's m? What makes this different so that it can amplify linearly? That is none other than the gain. The gain, the open loop gain, or the closed loop gain, like you'll see in just a second. Okay, so we've covered this. I just want to show you what saturation looks like in the case that, if we input a sine wave into this amplifier, what happens if it exceeds the supply rails? So let's say we have this small sine wave, it goes through the op amp, now it's a really big sine wave. Happy days, right? Wow, life is good. But it's exceeded our limits. Oh no. Minus VCC is here, and plus VCC is here. So what does that mean? That means it's been saturated at these limits, so it can't exceed these supply rail limits. So your output would actually look like this, which is obviously, as you might guess, unideal. We don't want that to happen. It's kind of a poor case if that were to happen. That's one thing I want to make clear. We also have some, I suppose, ground rules of the op amp. So we have an open loop gain when there is no feedback of the op amp. And this is really big. In the ideal case, it's actually infinity. We also have an input impedance. So within these inputs, there's an impedance, and it's a very large impedance. Typically infinity in the ideal case, very big. However, we have an output impedance which is very low, about 0 in the ideal case. So what does that mean? How can we put this into words that we can understand? So that means, these two rules in particular, so that means no current can flow into these inputs, but we can certainly have an output current at the op amp. And there's another rule. If we have negative feedback, I'll just move here. If negative feedback, V minus will try to match V plus. This is a very key rule. So when I shortly discuss with you what we call the inverting amplifier, you will see exactly what I mean and how we can leverage these rules actually in our favor so we can properly amplify signals. So now that I've covered that, but how do we know which feedback to choose? Because we could have a negative feedback, but what will stop us from doing a positive feedback? What's the difference? Okay, so for example, I have this measuring tape, which is the signal, and my hand is the set point, is the target of the signal. So if I throw this up, it will come back down. So this is negative feedback. I throw it up, it's, oh no, I'm too far from the set point. What am I going to do? So it will actually go down. It will subtract the error. And let's say my hand was transparent. Oops, now it's gone too low. Now it'll go back up again, down, up, until it hovers very closely around the target set point. So it would look like this. Like that. So the error would be less and less. But if we have positive feedback, then the opposite is true here. It would end up looking like this. So if I threw my measuring tape, it would go higher. If I threw it just a little bit, it would go higher, lower, a lot higher, a lot lower, until it hits my floor and it hits my ceiling, and I don't want that to happen, okay? So that's the basics of negative feedback, positive feedback. As time goes on, the error will be less. As time goes on in positive feedback, the error will be more. Negative feedback, positive feedback, okay? But there are some uses for positive feedback. We can leverage that as well, but this is a story for another day. So now I've covered these basic principles of the op amp. I guess for a bit of an FYI, there are lots of transistors that we use in an operational amplifier. It's not just a box where we throw a signal in and we get a nicer one, a nice bigger one out. there's a lot more inner workings of the op amp than you might think. So if you want to read it in your own time, I can name a few of these things for you right now. We use these transistors in specific ways. So you might want to look at the long tail pair, the current mirror. These two, how do I say, circuits, I guess. The ways that we've used the BJT transistor, that we've used them in the op amp. So you can look at these if you want. I'll be covering these in future videos, just not today. Okay, so without further ado, let's look at the inverting amplifier. Okay, so of course we're going to need one of these, an op amp. Okay, here's the input. Here's the output voltage. Here is the feedback resistor. Here is the input voltage, the input resistance, and here is the ground of the non-inverting terminal. So let's take a look at how this is connected. Why have we connected this to ground? It actually makes life a lot easier in the analysis side of things. So because this is ground and we have negative feedback, this rule says that V minus will try to match V plus. But since V plus is 0, we're going to have 0 here as well. So 0 volts, and we have a common nickname for this. We like to call it the virtual ground. Like, think virtual reality. It looks real when you have the VR headset on, but it's not actually there. The same way that there is no ground connection here at the non-inverting terminal, but it may appear to be because of this property. It has no connection to ground, but it has the same potential as ground, which is 0 volts. Okay, so now we've covered that. Let's call this area node A. This will be of great interest. So if we do a Kirchhoff's current law analysis at node A, so let's look at the input currents. That would be equal to V in minus V minus divided by R in. But look, because of this rule, the virtual ground, negative feedback, 0 volts there. So this is 0 volts really. So this is also equal to V in divided by R in to get the input current. But because of this rule, the input impedance is very large, almost infinity, very big. So it's a hard day's work for the input current to make its way into the op amp. So it will just find another way around to get to the output. It will follow this way. The input current will actually flow through the feedback resistor to the output voltage. So using this, we can also do an analysis here that V minus minus V out divided by RF should be also equal to the input current. But hold on, this is also 0 volts. So we can make that simplification again. Minus V out divided by RF is also the input current. So now that we've found this expression and this expression, so now we have an output voltage and an input voltage, we can now start to rearrange for the gain. So minus V out divided by RF equal to V in divided by R in. If we just rearrange these, then what we get is V out over V in equals minus RF over Rn, which will give us the closed loop voltage gain of this op amp. Very important equation. So this covers the analysis that you might expect to see with the inverting amplifier. So now I will just ask you a couple questions to test your theoretical knowledge of the inverting amplifier, okay? Okay, so here are two questions I have for you to try. So for question 1A, choose, I want to make this clear, realistic resistor values to achieve a gain of -4. And for question 1B, using this gain, and given that the supply rails are plus 14 volts and minus 10 volts, would the output voltage saturate? Okay, so just give those questions a quick try and I'll go over the answers with you. Okay, so let's choose, or start with question 1A. Choose resistor values that are realistic to achieve a gain of -4. So as you might recall, that AV for the inverting amplifier is equal to minus RF over Rn. Okay, so if we just choose like 4 ohms divided by 1 ohms, this is theoretically correct, but in the real world, and according to the rules, that's not correct. Because as you may see here, that this input resistance is now responsible for the rule of Zin must be theoretically infinity. So if you choose 1 ohm, that's closer to 0, never mind infinity, so that's just not going to work. So choose sensible values, so in the order of kilo ohms, for example. So you could do like RF is equal to 8 kilo ohms and Rn is equal to, let's say, 2 kilo ohms to achieve a gain of -4 with realistic resistor values. Okay, so that's question 1A done. So given that now the supply rails are plus 14 and minus 10 volts, would VO saturate? The answer is yes. So let's see why. So we have a gain of -4 and the input is 3. As you might recall from the straight line equation that we found in the transfer characteristics, VO is equal to AV, AV times V in. Okay? So if this is -4 and this is 3 volts, we get -12 volts. So this has exceeded the lower limit of our supply rail. So the answer is yes. So these are the main questions I have for today's video that will test your understanding of the inverting amplifier. And in the future, I will be covering more versions of the amplifier, more configurations. Okay, so I hope you enjoyed this video and learned something new. Thank you very much for watching.